Hi students. Okay, today our topic methods to reduce quadratic form to canonical form and how to convert given quadratic form to canonical form by using some methods are given. Here three methods are given. The first method is orthogonal transformation. Second one is diagonalization transformation. Third one is Lagrange's transformation. And in the previous lecture already we finding rank, index, signature and nature by using the eigenvalues of the coefficient matrix. That is one of the procedure, one of the way. So next how to finding rank, signature, index, nature of the given quadratic form by converting into canonical form. So after convert canonical form, then finding all rank, index, signature and nature. So how to finding? So using here first method here. So the first method is orthogonal transformation. So what is the definition of canonical form? So in the quadratic form, all are eliminating the product terms. That is, for example, xy, yz, zx, all are terms eliminating, remaining the sum of the squares of same variables, and x square, y square, z square. The sum of the that all squares of the same variable, that is called canonical form. So how to convert that one? First method is orthogonal transformation. So see that here, if q is equal to x transpose x is a quadratic form and there exists orthogonal transformation. So orthogonal transformation means x is equal to py. So where p is a orthogonal matrix and this is a transformation, and p is a non-singular matrix, that is a modal matrix which is transform the given quadratic form x transpose ax to the new form. This is the new form is summation I is equal to 1 to r lambda I by I square. And I must look at lambda 1, lambda 2 up to so on lambda r. And they are coefficients. When you go to diagonal elements and in the new form, that is a canonical form. మన canonical form లో ఓన్లీ మనకు diagonal elements మాత్రమే ఎగ్జిస్ట్ అవుతాయి మ్యాట్రిక్స్ ఫామ్ లో. So remaining new variables, you have to finding the new variable. Assumption y1, y2, y3 up to so on. y1, y2, y3 up to so on. That is a new variables. So in the canonical formula only coefficient matrix is must be diagonal matrix. That is diagonal elements only eigenvalues of the coefficient matrix of the given quadratic form. ఇక్కడ eigenvalues exist అవుతాయి. That eigenvalues must be equal to the eigenvalues of coefficient matrix. So this is the converted to canonical form using this transformation. This transformation is orthogonal transformation. Okay, now this is the canonical form finding by using orthogonal transformation. Okay, so that is equal to, see the one of the example. So reduce the following quadratic form to canonical form by orthogonal transformation. Also find the rank, index, signature and value class, that is the nature of the quadratic form. Q is equal to 3x square plus 5y square plus 3z square minus 2xy minus 2yz plus 2xz. Okay, in this method how to finding, what is the procedure? Using x is equal to py and p is equal to here orthogonal matrix. Orthogonal matrix means p transpose is equal to p inverse కదా. అంటే ఆల్రెడీ మనకు ప్రీవియస్ యూనిట్ 2లో మనం ఫైండ్ అవుట్ చేసాం ఆర్థోగోనల్ విచ్ ఈజ్ ద డయాగ్నలైజేషన్. అంటే p ఇన్వర్స్ AP ఈజ్ ఈక్వల్ టు క్యాపిటల్ D డయాగ్నల్ మ్యాట్రిక్స్ కదా. సో హౌ టు ఫైండింగ్ డయాగ్నల్ మ్యాట్రిక్స్ హియర్? p transpose A into p. The p transpose is modal matrix. The modal matrix is must be the modal matrix formed by the eigenvectors. That is the eigenvalues finding. Next to finding eigenvectors, all eigenvectors must be linearly independent eigenvectors and also mutually orthogonality. And next to finding normalized. And for each eigenvector to finding normalized vector. Then after finding the normalized vector, then write P matrix, that is a x1, x2, x3 whose columns are linearly independent orthogonal eigenvectors, that is a P matrix. Next finding P transpose. Next finding P transpose A into P is equal to diagonal matrix. That diagonal matrix is only diagonal elements or eigenvalues of A. Then using x is equal to Py, then that using transformation you have to finding the new form, that is a canonical form. So that is a procedure. And first మనం find out చేయాల్సింది coefficient matrix, eigenvalues, eigenvectors, and verify the condition orthogonality. Next to normalized vector, next to matrix P, next to finding P transpose, next to P transpose AP is equal to diagonal matrix. That matrix choosing you have to finding the canonical form. Okay, now that is a lengthy procedure. So that is equal, first of all, given quadratic form. So that is equal to x transpose AX matrix form. So that is x, three unknowns, x, y, z. This is a coefficient matrix. X square, y square, z square is the coefficients. Diagonal elements 3, 5, 3. Next to xy coefficient minus 2 అంటే -1, -1. xz coefficient 2, +1, +1. yz coefficient -2, that is -1, -1. This is a x. So this is a coefficient matrix. Okay, now. So now finding the first eigenvalues. So characteristic equation is data of a minus lambda is equal to 0. You have to finding here 3 minus lambda -1, 1, -1, 5 minus lambda -1, 1 -1, 3 minus lambda is equal to 0. So this is a characteristic equation. Finding this, solving this equation, we getting the characteristic equation. Now solving equation, we getting the eigenvalues, lambda value, that is equal eigenvalues are lambda is equal to 2, 3, 6. So now here next finding for each eigenvalues we have to finding the eigenvectors. Same procedure. Yeah. Now to find eigenvector corresponding to eigenvalues 2, 3, 6. Same procedure. First for lambda is equal to, same procedure, that is a minus lambda is equal I into x is equal 0 kada, that is 2 a minus 2i lambda I into x is equal 0. This is a matrix equation. So a minus 2i into x is equal 0. So that is equal, say a matrix లో the diagonal elements -2 చేయాలి అవునా. So that is equal to simplification. So this one, this is homogeneous equation కదా. So matrix A is converted to the row echelon form. Same procedure. This element 0, this element 0. So we getting directly, I am telling here eigenvector corresponding to lambda is equal to, same procedure చేసేసాను already find out చేసాం many problems. So x is equal eigenvector minus k1, 0, k1. K1 common. So -1, 0, 1. That is k1 into x1. This is the x1 is the linearly independent eigenvectors. Without choosing the constant k1. This is a linearly independent eigenvectors. So next one, second eigenvalues for lambda is equal 3. The same procedure, a minus lambda I into x is equal 0. Lambda is equal 3 kada. A minus 3i into x is equal to 0. So that is equal to this matrix 3 minus each diagonal elements. Simplification is same, this matrix is converted to row echelon form after finding the solution. Okay, now we getting the eigenvector is, second eigenvector x is equal to k2, k2, k2. K2 common 1, 1, 1. So that is x2. This is the second linearly independent eigenvectors. Okay. Similarly, we have to finding the for eigenvalues lambda is equal to 6. So that is equal to third eigenvalues lambda is equal to 6. Same, a minus lambda into x is equal 0. A minus 6i into x is equal 0. So same matrix a minus 6 కదా, diagonal elements -6 చేయండి. That is equal to simplification. So next same, this element 0, this element 0, this element zeros by using row echelon form. So directly how to finding the eigenvector, third eigenvector x is equal to k3 minus 2 k3 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 common 1 minus 2 1 k3 into x3. So this is a third eigen, that is linearly independent vector, third linearly independent eigenvector corresponding to lambda is equal to 6. So therefore 3 eigenvectors are mutually orthogonal vectors. And then why 3 eigenvalues are given getting distinct eigenvalues. So eigenvalues are distinct, automatically 2 corresponding eigenvectors is always mutually orthogonality. So in case eigenvalues not distinct, then again verify the condition is orthogonal or not. If not orthogonal, any vector is not orthogonal, then finding the new eigenvector, that is new linearly independent eigenvector which is corresponding to orthogonal to remaining 2 vectors. That is a procedure already I told in the previous lecture. See that orthogonal no problem, direct we can choose. If not orthogonal, which one is not orthogonal, then finding the new orthogonal vector. Using the x1 transpose x2 is equal to 0, x3 transpose x1 is equal to 0. Using that condition, we have to solving that, we getting the new orthogonal eigenvectors. Okay na? Ee problem lo motham compulsory 3 eigenvectors mutually orthogonal. So this is a 3 eigenvectors, linearly independent, mutually orthogonal vectors. So next procedure, finding the norm, that is length of each eigenvector, normalized vector. So now length of the eigenvector x1. x1 means, length means square root of sum of the elements in the vector. Sum of the elements, first eigenvector minus 1 square plus 0 square plus 1 square. So that is equal to root 2. First length of the eigenvector x1. Next length of eigenvector x2, that is square root of sum of 1 square plus 1 square plus 1 square, that is equal to root 3. Next length of eigenvector x3. Sorry, this is x3 and some mistake, typing mistake. Length of the eigenvector x3, that is the square root of sum of 1 square 2 square 1 square minus 2 square 1 square, that is equal to root 6. Okay na? So now here normalized vector, and each element in the corresponding eigenvector dividing by its length, that is equal to normalized vectors. So x1 is equal to minus 1 by root 2, 0 1 by root 2. Okay na? x2 is 1 by root 3, 1 by root 3, 1 by root 3. Okay na? Next x3, 1 by root 6 minus 2 by root 6, 1 by root 6. So this is x1, x2, x3 are normalized eigenvectors. So next write modal matrix. What is the modal matrix? The matrix is whose columns are normalized vectors, that is equal to modal matrix P. So that is modal matrix P has normalized eigenvector as its column vectors, that is equal to, this is the modal matrix P. This is the first eigenvector, second eigenvector, third eigenvectors. Next finding P transpose. We know that D, P transpose AP. This is a diagonalizable matrix and formula, P transpose AP. Next finding P transpose find out chain. So this is a interchanging row and columns together, P. So this is a P transpose. This is a given coefficient matrix A, and this is a P matrix. Multiplying 3 matrices, we have to getting the diagonal matrix. The diagonal matrix is whose diagonal elements are eigenvalues of A, that is equal to here matrix N. This is a diagonal matrix 2 0 0 0 3 0 0 0 6. This is a diagonal matrix D. Okay. So next continuation. So using this transformation, x is equal to py is the orthogonal transformation here, and a py in the given quadratic form, the substituting x place low, py replacing, that is equal to So Q is equal X transpose AX here. This is a given quadratic form. In this one, substituting X place of PY replacing. That is PY transpose A into PY, that is equal to Y transpose into P transpose AP into Y is equal to P transpose AP is equal to already finding diagonal matrix D. So here Y is a new variable matrix. Assumption any new variables. That is y1, y2, y3 assumption. Okay. So that is equal Y transpose is matrix of new variables y1, y2, y3. So capital D is a diagonal matrix already finding 2 0 0 0 3 0 0 0 6. This is the Y matrix. Okay na. So observing here all are zeros, only diagonal elements together. And the diagonal elements and the coefficient of squares of the same variables together. 2 is the first coefficient of first variable squaring. 3 is the coefficient of squaring of second variable. 6 is the coefficient of square of third variable. That is equal to 2y1 square plus 3y2 square plus 6y3 square. This is the canonical form. And here products level chudandi yz, xz, zx, that is all are eliminating. This is only sum of the squares of the same variable. So this is the canonical form. Okay, in the canonical form, now finding here rank. Rank means in the canonical form the number of non-zero terms. Index rank means rank, the definition is in the canonical form the number of non-zero positive terms is rank. So that is rank, number of non-zero terms in the canonical form. 3 gana 2 3 6 all are positive, totally 3. Next index is the number of non-zero positive terms. So in the canonical term form number of non-zero terms alone and positive terms all are 3 positive together. 2 3 6 all are positive. So index is number of positive terms in the canonical form, that is 3. Next signature. Signature is the difference between positive and negative terms in the canonical form. Positive terms is 3, negative terms 0, and 3 minus 0 is equal to 3. So difference between the number of positive and negative terms in canonical form, that is 3 minus 0 is equal to 3. Next to nature. Nature means all terms in the canonical form all are positive, non-zero positive. That is the nature is positive definite. So that is equal to positive definite nature. Okay now, this is the orthogonal transformation method given quadratic form to reducible to canonical form. So this is a lengthy procedure. Every problem same. But here to every problem we are discussing the orthogonality vectors. After finding the orthogonal vectors must be orthogonal, not verify condition. If orthogonal, next finding normalized. If not orthogonal, next finding the new orthogonal vector. That is the important here. Okay. Yeah, thank you. This is the first method completed. For more videos, please do subscribe my channel, like and share it. Thank you.